use. We learn a lot about like a 30-degree angle, a 60-degree angle, a 90-degree angle, 45-degree angle, because those end up providing us ratios that are really nice to deal with. You know, if I had a choice to use, you know, for instance, let's just look at the values here. If I look at, let me make sure I'm in the right mode. Okay, so sine of 30 is going to be a half, right? Would you rather use that ratio or would you rather use this ratio? You'd rather use the 30, right? 102, or sorry, 1 over 2 is a lot more convenient to use and manipulate than 0.5735764,364, right? However, what we learn with sine of 30 and the calculations that we do and the procedures that we go through with that calculation can be done with sine of 35 as well, right? So we'll have formulas later on throughout the year that we do a lot of work with 30, 60, 45. But that exact same work can be done with any angle that we put in there, all right? So early on, we're going to use these convenient values just because they're convenient, all right? And they come out to have really, really nice ratios. But I wanted to show you, I don't know if we got to this yesterday in this class or not, but I wanted to show you that when we take a 30-degree angle, regardless of what the side lengths are, okay, they're going to just work out, and it's because of similarity and proportions and that kind of stuff, but they're going to work out to be in the same ratio to one another as any other triangle that has a 30-degree angle. So if I look at this triangle, right now we've got a side length of 6. In the way this is set up, that's a side length of 3.46. Right angle, so Pythagoras tells us this should be 6.93. Okay? If I take over here, you see what I've done? I've taken K divided by I. You see that in that yellow box? Well, K is this length here, and I is that length there, right? So it's taking K divided by I, which is the opposite side divided by the hypotenuse, right? And it's the opposite side in regards to this 30-degree angle. So when I take K divided by I, I'm actually finding the sine of 30 degrees. Does that make sense, everybody? Okay. Here I'm taking K divided by J. So K divided by J. K divided by J, that's opposite divided by adjacent, right? So that number right there is giving me the tangent value of 30 degrees. And if I take radical 3 over 3, take that number right there, and divide it out and get a decimal, just to kind of prove it to you, square root of 3 divided by 3 gives me that number right there, 0.58, right? So that is K divided by J is radical 3 over 3. And then this cosine here is adjacent divided by hypotenuse, okay? So it's J divided by I, okay? And if I take 6 divided by 6.93, it's radical 3 over 2, okay? Which is about 0.86, okay? Is everybody all right with that? Now what I wanted to show you is that when I change this triangle and I mess up with those values of J, K, and I, they're completely different values of J, K, and I, right? But are these ratios of K divided by I, K divided by J, and J divided by I, are they still 1/2 radical 3 over 2 and radical 3 over 3? Okay? So it doesn't matter, come down to this one, it doesn't matter if I take, 4 divided by 4.62, I'm still getting this number right here. Okay, I'm still getting that 0.87. Does that make sense, everybody? And the reason that all is true, let's get back to a little bit of a bigger triangle here. Maybe. Forget which points I'm using to adjust this. There we go. The key thing is it's got to be a right triangle, right, to get these ratios. If it's not a right triangle, so there, those ratios are not 1/2 radical 3 over 2 and radical 3 over 3, right? And now we will eventually deal with these values for this angle. This angle right here is a 78.69 degree angle. So when we have a 30, 78.69 degree angle, and then that angle, we should be able to figure out these values. You guys remember the law of sines, law of cosines? That stuff will allow us to find these values. But with a right angle, we should always get those. But the reason is, we've talked about put that triangle right there. Would you agree that that triangle right there has a 30-degree angle in it? Does it have a 90-degree angle in it? Okay. Does the overall triangle have a 30-degree angle in it? Does it have a right angle in it? So what that tells us is that these two triangles are similar by the angle-angle similarity postulate. And because they're similar, if you remember what similarity meant to us in geometry, if we've got, let's say, we should call this triangle ADB, and we say triangle ADB is similar to EGB. In geometry, what that told us is that when I take AD, take this segment here, and I compare it to EG through division, that should give me the exact same ratio as when I compare DB to GB. Does that make sense? Which should give me the exact same ratio as AB compared to EB. All right? So if I do those things, if I look at AD, which is K, let me come up here and we're going to see some numbers here. Okay, so AD is this amount here, 3.46. So I'm going to take that number and I'm going to compare it to EG, which is, they're calling B sub 1. Okay, divided by B1. If I hit that, I get 1.5. Okay, so they're saying this ratio is 1.5, meaning that if I know this length here, I should be able to multiply that length by 1.5, and it's going to give me that length right there. Does that make sense to everybody? Okay. Or if I know that length, I should be able to multiply by 2/3 to get that length. Is that all right? Multiply by the reciprocal to reduce it. But that ratio of AD divided by EG should be the exact same ratio as DB divided by GB. So DB is I, and GB is E. So I divided by E should give me the same 1.5 back. And we should be able to do the exact same thing from A to B, which is J, and divide that by E to B, which is G sub 1. Should get 1.5 back. I don't know why it puts it as a fraction, but it's still 1.5, right? Okay. So that's the reason why when we look at these triangles, we are always getting the same 1/2, radical 3/2, radical 3/3 back, is because these things are always in proportion to one another. If I change things, if I change this triangle, let's say, we look at that triangle compared to this one, okay? Now, it's not the same 3/2 or 1.5, but it's 1.75. Is 1.75, 1.75, and is that 1.75? Yeah, okay. So the ratio, these two triangles are similar, so these ratios are equivalent, and that's essentially what's allowing us to make the argument that regardless of the triangle, if I have a 30-degree triangle, 30-degree angle in my right triangle, these ratios are true and always consistent for the adjacent side divided by, or so the opposite side divided by the hypotenuse, adjacent side divided by hypotenuse, and the opposite side divided by adjacent side. Is that all right with everyone? Okay. And I think that's important to look at and think about and remind ourselves that when, in 2 weeks, 3 weeks, 4 weeks from now, when we're using these ratios in a question, it shows up the cosine of 60 degrees, and we automatically know what to put in. We automatically put in like radical, cosine of 60 is 1/2. We automatically put in 1/2. Okay. Well, where is that coming from? That's coming from that triangle stuff. Okay, and that's the reason for it. So I don't want you to lose sight of that as we move on throughout the year, because it does happen. I mean, we're going to be hopefully try to eliminate this, but you'll be robotic at some point where you say, oh, cosine 60, I know what that is. Sine of 30, I know what that is. Tangent of 45, I know that's 1. But why do you know those things? And I want to make sure that you're in your back of your mind, you've always got a reason why those values are what they are. Okay? I want you to understand that your calculator is not just coming up with just random values, or it's not magical numbers have been coded into your calculator to pop up, and why do we use them, why we don't use them. I want you to understand that relationship. These are some things on the PDF that I don't necessarily like this chart, but I want to show it to you. Don't write it down. If you want this chart, if you want to use it, which is fine in your homework, use it. But if you know how to draw a 30, 60, 90 triangle, a 45, 45, 90 triangle, that is going to take place of this chart for you, I think, for the most part. There are some things in there that are not seen in a 45, 90 or 30, 60, 90 triangle. They're the 180 degrees, the 270 degrees, and a lot of times we don't deal with the 90-degree angle. But this chart is providing you all those convenient ratios. So if I were to take my calculator, put it in one of those two modes in those left two columns, and I type in, like, say, sine of 30, okay, it's going to spit back 0.5 or 1/2. If I type in sine of 30, or sorry, cosine 30, it's going to spit back 0.866, which is that radical 3 over 2 number. Okay. If I type in cosine 45, it's going to spit back 0.707, which is radical 2 over 2. Tangent of 45 is going to be 1. Okay, that's a set of convenient values that we're going to use over and over again, and those are the nice values that your calculator can kick back to you. Is that all right there, Ron? Now you don't have to. What's this? You don't have to memorize that chart when we get to. Have you guys in physics used the unit circle? Okay. We're going to get to chapter 6, and we're going to start dealing with these angle measurements using a different approach, and we're going to use circles. And it will have a much more convenient way of not memorizing, but developing these values, these ratios, using the circle instead of this chart. Okay. So don't worry too much about this chart, but it does produce and provide, I think, those convenient values that you can see over and over again. They're the nice ones your calculator gives you. Okay. The one thing that I want you to understand is that your calculator, when you type in cosine of 60, actually let's do sine of 60, your calculator is not going to give you that radical 3 over 2 in that format, right? It's going to give it to you in a decimal version. A lot of times in WebAssign, if they're using 30 degrees, 60 degrees, 45 degrees, they're going to want exact answers. Throughout the course, if I ever write something on paper and there's a 30, 60, 45 degree angle, we want to write them as exact. Okay? So we're going to use the radicals and that kind of stuff. So that's maybe why this chart is there, to help us remind those things. But if you know your 30, 60, 90 templates, your 45, 45, 90 templates, it shouldn't be too big of a deal. And I'll put those up here in a moment. Yesterday we started talking about sine, cosine, and tangent, right? So something that we hopefully have kind of drilled into our minds, and it's just second nature now in developing those things. Okay. However, remember that it's defined off of a particular angle. You have to state what angle you're looking at first, and then the three sides are based off of that angle. When we deal with their reciprocals, if I look at sine and I look at the ratio right underneath it, I don't think we talked about this with you guys yesterday. If I look at this ratio here and that ratio there, okay, they are reciprocals, right? So that tells me that sine of theta and cosecant theta are reciprocal ratios, reciprocal trig ratios, okay? Which is a very important relationship to understand. If I look at cosine and secant, look at that middle column, okay? The ratio is a reciprocal on the right-hand side, right? So cosine of theta is the reciprocal of secant, and secant is the reciprocal of cosine, right? That's something to kind of think about. If I have 3/2 as a number, its reciprocal is 2/3, right? 3/2 is 2/3 reciprocal, but 2/3 is 3/2 reciprocal, right? It's a two-way street. Okay, so cosine is reciprocal of secant, secant's reciprocal is cosine. And then obviously we get the tangent and cotangent. The tangent and the cotangent one, those are obvious. People don't mess those up because they have the word both of them have the word tangent in them. Okay. The way I remember reciprocal functions, or reciprocal, I'm going to hear me say functions a lot because we do eventually start talking about functions, and it's just built into me to say function for some reason. I should be saying ratio. But the way I remember it is that with reciprocals, the first letters should never match up. So C should never match up with a C. Does that make sense? Okay. C and S go together, so cosine and secant. And then S and C go together for sine and cosecant. I know I've got those four. If I want to compare them in regards to reciprocals, just make sure that the S's don't pair up, okay? And the C's don't pair up. Does that make sense? There might be other ways that you can remember that. It's just the way that I do it. Now, if you look at your calculator doesn't have any of those buttons. Your calculator doesn't have a cosecant. Your calculator doesn't have a secant. Doesn't have a cotangent. Okay, so this is what we want to do with our calculator. If we think about what the definition of a reciprocal is, so let's say that I have M as my ratio, then its reciprocal is 1 over M, right? Okay, so if I have then sine of theta as my ratio, it's and that's sine of theta over 1, correct? Would you agree that its reciprocal is 1 over sine? Does that make sense to everybody? Okay. It's just that we have taken, we see that a lot, we see that ratio a lot, 1 over sine, so we rename it and just say, well, that's the same thing as cosecant. Okay. So at any time that you see cosecant, you need to evaluate it with your calculator. So for instance, maybe they ask you what the cosecant of 30 degrees is. Okay? You're going to type in 1 divided by sine of 30. Is that all right? Because your calculator does not have that cosecant button on there. So let's just do an example. Cosecant of 30 degrees. Okay? Well, we're going to rewrite that as 1 divided by sine of 30 degrees. Okay? 1 divided by sine of 30 degrees. And if you type in your calculator will evaluate it, but let's do it this way. Do you know what the sine of 30 degrees is? What is the sine of 30 degrees? 1/2. So I've got 1 over 1/2, right? Well, 1 over 1/2 is 2. Okay? And calculator-wise, the one thing you got to pay attention to is the mode that you're in. So I'm going to make sure I'm in degrees, and I am. I'm going to type in 1 divided by sine of 30 gives me my cosecant to be 2. Okay. There are other ways kind of to evaluate this. You could say, well, I know this is kind of the way I do. I'm not saying this is right, but if they ask me cosecant of 30, I never really do that. I do sine of 30. I know sine of 30 is 1/2, right? And now I know these two things are reciprocal, so what's the reciprocal of 1/2? 2. Okay. I just think that's maybe, it's doing the exact same thing. I just, logically, it makes more sense to me to write it that way. It's up to you, but if you're going to use your calculator, which at times you're going to have to, you don't have the secant, you don't have the cotangent buttons, you don't have the cosecant. So you need to use the 1 over sine, cosine, or tangent, respectively. Is that okay? Let's see here. just drawing real quick the the 30, 60, 90 triangle. Remember, across from the 30 degree is always your smallest side. Your hypotenuse always has to be your biggest side, and it's twice as big as what this side was. And then across from 60 is always n radical 3. And then what's nice about that, if you think sine of 30, it's opposite over hypotenuse, right? N over 2, and what happens to the ends? Cancel out. So hopefully that shows you that it doesn't matter what n is. It doesn't matter how big that side is. It doesn't matter how big that hypotenuse is. That n is consistent. That 2 is consistent. And you're always going to get them to divide to be 1/2. And that's where we're seeing back in this chart here, sine of 30 is that 1/2 there. But I think it's a good idea maybe to have that template in your notes somewhere. The other template, if you remember, was the 45, 45, 90 triangle. And we know those two things are the same. It's an isosceles right triangle, correct? So sides have to be the same. And if I use Pythagoras, if that's n and that's n, I've got essentially n squared plus n squared, which is 2n squared. Which then using the Pythagorean theorem to solve for the hypotenuse would give me n radical 2. So that's the template for that. And that essentially takes care of the chart that I was showing you. You know, and it asks, what is the tangent of 45? Well, the reason the tangent of 45 is 1 is because if I go opposite divided by adjacent, don't I get n divided by n? What's n divided by n? It's just 1. Okay. Regardless of what n is, n could be 400. Okay, and I got 400, 400, 400 radical 2 as side lengths, and 400 divided by 400 always goes down to 1. So that's something maybe you should have in front of you as we progress through this, at least this section, and it's going to help us introduce the information that we learned in Chapter 6. It's those two triangles are really the foundation of the unit circle, that thing I talked about earlier. So that I think one of the top 3 or 4 things that you take out of high school math is those two triangles. Okay? They're very useful in a lot of the other things that you do, calculus-wise, physics-wise. It's very, very, very important. Here they're going to say find the 6 trig ratios. It's pretty simple, pretty straightforward. If you know your 6 ratios, if you know SOHCAHTOA and then the reciprocal ratios. If I say I want to find sine of theta, I want to find cosine of theta, and I want to find tangent of theta. I think if you structure and organize things correctly, this isn't going to be too bad. What is the reciprocal of sine? What always goes with that? Cosecant. Okay. And what goes with cosine then? Secant. And tangent always pairs up with cotangent. Now, that is just if I'm asking for the 6 trigonometric ratios, and we look at them as reciprocals of one another. There will be relationships eventually that we talk about with those two. Okay, sine and cosine. There will be a relationship that we look at between these two, secant and cosecant. And there will be an additional relationship that we look at between those two, which are tangent and cotangent. And if you think about the names, they repeat themselves, just half of them have the word co in front, right? Okay, so that'll be important. There's a reason for that. But looking at this in this case, you just want to find the 6 trig ratios. So sine of theta, remember theta is the angle that you're interested in. So everything is defined off of that. So that's my opposite side, that's my adjacent side, and that's my hypotenuse. Okay, this is kind of a fundamental problem that will repeat itself over and over and over again throughout the course, just having different aspects to it, maybe using different formulas, maybe using different approaches. But if you can understand what we're doing here, it gives you a pretty good chance at those other questions later on. Sine is opposite divided by hypotenuse, right? So sine is 2/3. Cosine is going to be what? Yep, root 5 over 3. What's tangent going to be? 2 divided square root of 5. Now, I'm a person, I'm not going to rationalize that yet. Maybe show you why here in a moment. But when we write our answers in WebAssign, they're not going to want this radical 5 in the bottom. When we write it on a test or a quiz, I'm not going to want that radical 5 in the bottom. So we'll change that here in a moment. But what is the reciprocal then of sine? It would be 3/2. What's the reciprocal of cosine? 3 over radical 5. And now what's the reciprocal of tangent? Radical 5 over 2. See how when I did that reciprocal, it kind of rationalized that already for me? Okay, which is nice. But I still have a denominator here of radical 5 and a denominator there of radical 5. Rationalizing those means to multiply by a convenient factor of 1, right? Radical 5 over radical 5 is convenient factor of 1. And what happens there is it gives me 2 radical 5 up top, and it gives me what on the bottom? 5. Here's the reason I rationalize at the end, is because if I would have rationalized that value first, and then found the reciprocal of that pink value, I have to then rationalize this. Does that make sense? So I'm just thinking ahead, trying to save myself a little bit of work. It's not too bad. It's going to be 3 radical 5 over 5. And you start to see it. The more you do of that rationalizing, the more you're going to see the patterns and the fact that basically we just took the radical 5, put it up top, and then took away the radical on the bottom. But those evaluate to be the same thing. So 3 divided by radical 5 is the exact same thing as 3 times radical 5 divided by 5. That's the way they're going to want them, and that's the way you're going to want to deal with them, because eventually the algebra that we're going to do by taking those values and placing them elsewhere, maybe in equations or whatever, it's going to be so much more convenient to take 3 radical 5 over 5 and deal with it than it will be to take 3 over radical 5. Okay? Is that doable? Is that okay? Pretty easy, straightforward? Okay. Let's see here. Do those ratios change if I talk maybe about that angle there? Those ratios will change, won't they? Because this is now going to be the opposite side, and that's now going to be the adjacent side if I'm interested in looking at the angle alpha. So make sure that as we go through these problems, you're always cognizant of the angle that we're using. Pay attention to that angle. This is another question that is going to repeat itself over and over and over again throughout the course. This is kind of the easiest version of the question that we'll see. But it says, if cosine of theta is equal to 3/4, sketch a right triangle and find the other 5 trigonometric ratios. The thing here, and the reason this is one of the easier questions, because it doesn't give you any specifications on where your triangle has to show up, what type of orientation it has to be. So it could be any right triangle you want. You can take this thing, you can flip it, you can rotate it, you can do whatever you want. What you come up with is going to be the exact same thing that I come up with. But it's going to have an angle theta in it. So I'm going to, and you can use any angle you want, as long as it's one of the acute ones. So let's say that's theta. They're saying that cosine of that angle right now is 3/4. Well, cosine is adjacent divided by hypotenuse, isn't it? What they're telling you there when they say cosine equals 3/4, when they give you that ratio, they're telling you 2 side lengths of your triangle. Now, they're not telling you exactly what they are. So when I say adjacent is 3 and hypotenuse is 4, that's their ratio. So they could be 6 and 8. Does that make sense? It could be 9 and 12. That still reduces to a 3/4 ratio, correct? But everything that I learned about this 3/4 ratio would be as true for a 6 and 8 ratio or a 9 and 12 ratio. Now, if my goal is to find the other 5 trig ratios, I need the sine of theta. I need the the tangent of theta first. We're going to need the secant of theta. We're going to need the cosecant of theta, and then the cotangent of theta. Well, if I'm going to use the sine, I need the opposite side, right? I need this side right here. How do I find that? Okay, Pythagorean theorem says 9 plus x squared is going to equal 16, right? So x squared is going to equal 7. X then is equal to root 7. So radical 7 there. And then we can go find opposite divided by hypotenuse. So radical 7 over 4. We can do opposite divided by adjacent. Radical 7 divided by 3. We can do secant, which would be the reciprocal cosine, right? So once we get these 3, we can kind of stop looking at the triangle, and we just flip these fractions. So 4/3. 4 over root 7, which is going to become 4 root 7 over 7. And this one's going to be 3 over root 7, which becomes 3 root 7 over 7. Now my question to you is theta a 30-degree angle? What ratio should have shown up if theta was 30 degrees? You should have gotten a half, you should have gotten radical 3 over 3, you should have radical 3 over 2, those things, right? Is theta 45 degrees? If it's 45, you should have gotten ratios like radical 2 over 2 and 1, right? Okay. So that just tells us that theta is not one of those special angles that we talked about. If we wanted to, and I'm not going to ask you to do this right now, but you should have some understanding, maybe some things we remember from trigonometry, or sorry, not geometry. If you know the ratio, if you know that cosine is 3/4, and you could use this for any one of these, but if you know cosine is 3/4, that means that you know the ratio, you know the ratio for some particular angle, right? We just don't know that angle. Well, normally, if I type in like cosine of 30, it's going to spit back the ratio that goes with the 30-degree angle, right? Well, if I use cosine inverse, so I hit second cosine, now what you type in, and now you type in the ratio, and what's it going to spit back to you? The angle. So if I type in 3 divided by 4 as my ratio here, it spits back 41 degrees, okay? So any triangle, any right triangle, now that's going to be probably a number that goes on forever and never ends. But any angle with approximately a 41.4096221 angle, or degree angle, is going to have a 3/4 ratio for the adjacent side of the hypotenuse. Now if you type in second sine of this ratio, root 7, divided by 4. Make sure your 4 is not in that first parenthesis with your radical 7. Hit enter. It should give me the same angle back. Okay. Questions on that? We're good? I'm not going to ask you. I think you guys can do this. Just go to your calculator, type in tangent 40, see the ratio they give you back. Cosine 40, see the ratios. Now those numbers are ugly. 40, 20, 14, 80. Those are ugly numbers. So you're going to get decimals back that you have to leave as decimals and round at some point. What I want you guys to make sure you understand, and the reason this is there is when you grab a calculator out of the calculator's up here on my register, somebody else has used those before you, right? Somebody else's question, their last question they might have done, might have been in radians. But the first question you are doing on your test or quiz might be in degrees, right? Well, if you just start arbitrarily working with that calculator and start doing your calculations, stop looking at the mode, there's a 50-50 chance that you're going to be wrong, right? Because of the mode that you're in. So be very, very cautious that every time you grab a calculator in trigonometry, That's the first thing you want to do. What is my problem talking about? Does it have degrees in it or does it have radians in it? And then I go to my calculator and I change my calculator to that. Okay? Especially here pretty soon, my geometry students are going to start doing this stuff as well. My geometry students are always going to do stuff in degrees for the most part. Okay? So they're going to change all the calculators to degrees. You might get to your test or quiz and everything's in radians, but you never change. It's always 2 or 3 people every year. I give a quiz that it's all in radians, and they never change their calculator to degrees. Okay? Or vice versa, and they miss some points. They don't miss the whole thing because I'm kind of nice, but they miss some things for not paying attention to that detail. This question here says, when it says solve a triangle, all they're asking you to do is find all the missing parts. Okay? So if it has a special degree in it, a special angle measurement, the suggestion I have is to leave it as exact values. So we should know that in any special right triangle that has a 30-degree angle, that's 30. Okay, so this side here would be our n, right? This would be 2n, and this would be n radical 3. So what I always do is I always take that, and I try to lay it on top of the triangle that I'm dealing with, right? And where do we see a link in regards to being able to solve an equation? So I'm saying, view it this way, just for time. Does this hypotenuse match up to that hypotenuse? Yes. So we're saying that 2n should be the same thing as what? It should be 12, right? We create that little equation that 2n is 12. So then what is n? 6. So if n is 6 in our red triangle, n is what segment? It's BC, or A, right? Lowercase a. So I now know that to be 6. And then B is this n radical 3 side, so n was 6, so this becomes 6 radical 3, right? Okay. Now, there's other ways you could do it. You could use SOHCAHTOA. You could use SOHCAHTOA, and if I go, let's just say sine of 30 degrees, let's say I didn't know these two things. I say sine of 30 degrees is equal to opposite over hypotenuse, right? So A over 12. How do I solve for A? Multiply both sides by 12, right? What is our calculator going to evaluate that sine of 30 to be? 1/2. What's 12 times 1/2? It's that 6 right there that we get, right? The only issue that we have here is that when I want to do, I want to find B, I'll do cosine of 30 is equal to B over 12. So I get 12 cosine of 30 is equal to B. My calculator is going to spit back that B is like 10 point some number. 12 cosine 30. Check my mode real quick. Spits back 10.39, right? Well, we found it earlier as 6 radical 3, correct? Is that the same thing? Well, if I take 6 radical 3 and type that in, hit enter, it is the same thing. The only issue is if I don't learn the right triangle, the 30, 60, 90 aspect of things, and they ask me to leave my answer as an exact answer, you're going to really struggle taking that 10.39 number and changing it over to 6 radical 3. Don't know that you're going to be able to do it. Everybody on the same page there? So make sure that when you see 30-degree angles, 45-degree angles, 60-degree angles, you're thinking special right triangles, and they're probably going to want you to leave it as an exact answer. There's going to be some homework questions, and if we need to talk about them later on, we can. But there's some notes here. You guys remember talking about angle of elevation and angle of depression, measuring the heights of like flagpoles and trees and buildings and stuff like that, indirect measurement. You're going to see some story problems like that. On Monday, there is one question on there with the height of a flagpole that I want to talk about. But I think you guys have seen enough of those in Algebra 2 and in geometry that will be successful on those without instruction. This example here, you're doing the same thing we did in the last one, but now the degree is now turned into a radian, right? You can deal with it in radian form, or if you know pi over 6, what does pi over 6 convert to in degrees? 30 degrees. So if you want to convert that to 30 degrees because you're more comfortable dealing with a 30, 60, 90 triangle as a 30, 60, 90 triangle and not as a pi radical 3, pi radical 6, pi over 3, pi over 6, pi over 2 triangle, that's fine. Does that make sense? Okay. 30, 60, 90 is a little bit easier to understand, I think, for us right now. 5.2 is going to be due Wednesday, so you got some time on it. But we're going to move on to 5.3 on Monday. After a couple of questions that we discussed, we'll move on to 5.3.